For a topical guide to this subject, see Outline of the metric system. The metric system is an internationally agreed decimal system of measurement that was originally based on the marche des archives and the kilogramme des archives introduced by France in 1799. Over the years, the definitions of the meter and kilogram have been refined and the metric system has been extended to incorporate many more units. Although a number of variants of the metric system emerged in the late 19th and early 20th centuries, the term is now often used as a synonym for SI, or the International System of Units, the official system of measurement in almost every country in the world. The metric system has been officially sanctioned for use in the United States since 1866, but it remains the only industrialized country that has not adopted the metric system as its official system of measurement. Many sources also cite Liberia and Burma as the only other countries not to have done so. Although the United Kingdom uses the metric system for most official purposes, the use of the imperial system of measure, particularly among the public, is widespread, and is legally mandated in various cases. Although the originators intended to devise a system that was equally accessible to all, it proved necessary to use prototype units under the custody of government or other approved authorities as standards. Control of the prototype units of measure was maintained by the French government until 1875 when it passed to an intergovernmental organization, the General Conference on Weights and Measures. It is now hoped that the last of these prototypes can be retired by 2014. From its beginning, the main features of the metric system were the standard set of interrelated base units and a standard set of prefixes in powers of 10. These base units are used to derive larger and smaller units that could replace a huge number of other units of measure in existence. Although the system was first developed for commercial use, the development of coherent units of measure made it particularly suitable for science and engineering. The uncoordinated use of the metric system by different scientific and engineering disciplines, particularly in the late 19th century, resulted in different choices of fundamental units, even though all were based on the same definitions of the meter and the kilogram. During the 20th century, efforts were made to rationalize these units, and in 1960 the CGPM published the International System of Units, which, since then, has been the internationally recognized standard metric system. Features: although the metric system has changed and developed since its inception, its basic concepts have hardly changed. Designed for transnational use, it consisted of a basic set of units of measurement, now known as base units. Derived units were built up from the base units using logical rather than empirical relationships, while multiples and submultiples of both base and derived units were decimal-based and identified by a standard set of prefixes. Universality. At the outbreak of the French Revolution in 1789, most countries and even some cities had their own system of measurement. Although different countries might have used units of measure with the same name, such as the foot, or local language equivalents such as pide, feuille and voet, there was no consistency in the magnitude of those units, nor in the relationships with their multiples and submultiples, much like the modern-day differences between the US and the UK pints and gallons. The metric system was designed to be universal. In the words of the French philosopher Marquis de Condorcet, it was to be for all people for all time. It was designed for ordinary people, for engineers who worked in human-related measurements and for astronomers and physicists who worked with numbers both small and large, hence the huge range of prefixes that have now been defined in SI. When the French government first investigated the idea of overhauling their system of measurement, the concept of universality was put into practice when, in 1789, Maurice de Talleyrand, acting on Condorcet's advice, invited John Riggs Miller, a British parliamentarian, and Thomas Jefferson, the American Secretary of State to George Washington, to work with the French in producing an international standard by promoting legislation in their respective legislative bodies. However, these overtures failed and the custody of the metric system remained in the hands of the French government until 1875. Unit names are ordinary nouns, and although they use the character set and follow the grammatical rules of the language concerned, for example kilometer, kilocube, metro, each unit has a symbol that is independent of language, for example km for kilometer, V for volts, etc. Decimal multiples. In the metric system, multiples and submultiples of units follow a decimal pattern, a concept identified as a possibility in 1586 by Simon Stevin, the Flemish mathematician who had introduced decimal fractions into Europe. This is done at the cost of losing the simplicity associated with many traditional systems of units where division by 3 or 4 does not result in awkward fractions. For example, 1/3 of a foot is 4 inches, a simplicity that in 1790 was debated, but rejected by the originators of the metric system. In 1854, in the introduction to the Proceedings of the British Decimal Association, the mathematician Augustus de Morgan summarized the advantages of a decimal-based system over a non-decimal system thus: in the simple rules of arithmetic, we practice a pure decimal system, nowhere interrupted by the entrance of any other system. From column to column we never carry anything but tens. A common set of decimal-based prefixes that have the effect multiplication or division by an integer power of 10 can be applied to units which are too large or too small for practical use. The concept of using consistent classical names for the prefixes was first proposed in a report by the French Revolutionary Commission on Weights and Measures in May 1793. The prefix kilo, for example, is used to multiply the unit by 1000, and the prefix milli is to indicate a 1000th part of the unit. Thus the kilogram and kilometer are 1000 grams and meters respectively, and a milligram and millimeter are 1000th of a gram and meter respectively. These relations can be written symbolically as 1 mg equals 0.001 ag, 1 km equals 1000 am. In the early days, multipliers that were positive powers of 10 were given Greek-derived prefixes such as kilo and mega, and those that were negative powers of 10 were given Latin-derived prefixes such as centi and milli. However, 1935 extensions to the prefix system did not follow this convention. The prefixes nano and micro, for example, used prefixes with Greek roots. During the 19th century the prefix myria, derived from the Greek word I1/4 II to the first, was used as a multiplier for 10,000. When applying prefixes to derived units of area and volume that are expressed in terms of units of length squared or cubed, the square and cube operators are applied to the unit of length including the prefix, as illustrated here. 1 am 2 equals 2 equals 2 equals 0.000001 am 2, 1 km 2 equals 2 equals 2 equals 1 million am 2, 1 am 3 equals 3 equals 3 equals 0.0000000001 am 3, 1a. km 3 equals 3 equals 3 equals 1 billion am 3. Prefixes are not usually used to indicate multiples of a second greater than 1. The non-SI units of minute, hour and day are used instead. On the other hand, prefixes are used for multiples of the non-SI unit of volume, the liter such as milliliters. Realizability and replicable prototypes. The base units used in the metric system must be realizable, ideally with reference to natural phenomena rather than unique artifacts. Each of the base units in SI is accompanied by a Mersenne pratique, practical realization published by the BIPM that describes in detail at least one way in which the base unit can be measured. Where possible, definitions of the base units were developed so that any laboratory equipped with proper instruments would be able to realize a standard without reliance on an artifact held by another country. In practice, such realization is done under the auspices of a mutual acceptance arrangement. Meter and kilogram. In the original version of the metric system the base units could be derived from a specified length and the weight, mass of a specified volume of pure water. Initially the de facto French government of the day, the Assemblée Copyright Nationale Constituante, considered defining the meter as the length of a pendulum that has a period of 1 second at 45 degrees N and an altitude equal to sea level. The altitude and latitude were specified to accommodate variations in gravity. The specified latitude was a compromise between the latitude of London, Paris and the median parallel of the United States to accommodate variations. However, the mathematician Borda persuaded the Assembly that a survey having its ends at sea level and based on a meridian that spanned at least 10% of the Earth's quadrant would be more appropriate for such a basis. The available technology of the 1790s made it impracticable to use these definitions as the basis of the kilogram and the meter, so prototypes that represented these quantities insofar as was practicable were manufactured. On June 22, 1799 these prototypes were adopted as the definitive reference pieces, deposited in the Archives Nationales and became known as the Marche des Archives and the Kilogramme des Archives. Copies were made and distributed around France. These artifacts were replaced in 1889 by the new prototypes manufactured under international supervision. Insofar as was possible, the new prototypes were exact copies of the original prototypes, but used a later technology to ensure better stability. One of each of the kilogram and meter prototypes were chosen by lot to serve as the definitive international reference piece, with the remainder being distributed to signatories of the meter convention. In 1889 there was no generally accepted theory regarding the nature of light, but by 1960 the wavelength of specific light spectra could give a more accurate and reproducible value than a prototype meter. In that year the prototype meter was replaced by a formal definition which defines the meter in terms of the wavelength of specified light spectra. By 1983 it was accepted that the speed of light was constant and that this constant provided a more reproducible procedure for measuring length. Therefore the meter was redefined in terms of the speed of light. These definitions give a much better reproducibility and also allow anyone, anywhere with a suitably equipped laboratory, to make a standard meter. Other base units, none of the other base units rely on a prototype. All are based on phenomena that are directly observable and had been in use for many years before formally becoming part of the metric system. The second first became a de facto base unit within the metric system when, in 1832, Carl Friedrich Gauss used it, the centimeter and the gram, to express the units associated with values of absolute measurements of the Earth's magnetic field. The second, if based on the Earth's rotation, is not a constant as the Earth's rotation is slowing down. In 2008 the solar day was 0.002 as longer than in 1820. This had been known for many years. Consequently in 1952 the International Astronomical Union defined the second in terms of the Earth's rotation in the year 1900. Measurements of time were made using extrapolation from readings based on astronomy. With the launch of ESA in 1960, the 11th CGPM adopted the IAU definition. In the years that followed, atomic clocks became significantly more reliable and precise, and in 1968 the 13th CGPM redefined the second in terms of the frequency of a specific frequency from the emission spectrum of the cesium-133 atom, a component of atomic clocks. This provided the means to measure the time associated with astronomical phenomena rather than using astronomical phenomena as the basis from which time measurements were made. The CGS absolute unit of electric current, the Ampere, had been defined in terms of the force between two parallel current-carrying wires in 1881. In the 1940s, the International Electrotechnical Commission adopted an MKS variant of this definition for the ampere, which was adopted in 1948 by the CGPM. Temperature has always been based on observable phenomena. In 1744 the degree centigrade was based on the freezing and boiling points of water. In 1948 the CGPM adopted the centigrade scale, renamed it the Celsius temperature scale name, and defined it in terms of the triple point of water. When the mole and the candela were accepted by the CGPM in 1971 and 1975 respectively, both had been defined by third parties by reference to phenomena rather than artifacts. Coherence. Each variant of the metric system has a degree of coherency, the various derived units being directly related to the base units without the need of intermediate conversion factors. For example, in a coherent system the units of force, energy and power are chosen so that the equations, force equals mass a, acceleration, energy equals force a, distance, power equals energy/time, hold without the introduction of constant factors. Once a set of coherent units have been defined, other relationships in physics that use those units will automatically be true. Therefore Einstein's mass-energy equation, A equals mc2, does not require extraneous constants when expressed in coherent units. The CGS system had two units of energy, the erg that was related to mechanics and the calorie that was related to thermal energy, so only one of them could bear a coherent relationship to the base units. Coherence was a design aim of SI, resulting in only one unit of energy being defined, the joule. In SI, which is a coherent system, the unit of power is the watt, which is defined as 1 joule per second. In the U.S. customary system of measurement, which is non-coherent, the unit of power is the horsepower, which is defined as 550 foot-pounds per second. Similarly, neither the U.S. gallon nor the imperial gallon is 1 cubic foot or 1 cubic yard, the U.S. gallon is 231 cubic inches and the imperial gallon is 277.42 cubic inches. The concept of coherence was only introduced in the metric system in the third quarter of the 19th century. In its original form, the metric system was non-coherent. In particular, the liter was 0.001 am3 and the year was 100 am2. A precursor to the concept of coherence was however present in that the units of mass and length were related to each other through the physical properties of water, the gram having been designed as being the mass of 1 cubic centimeter of water at its freezing point. History. In 1586, the Flemish mathematician Simon Stevin published a small pamphlet called De Thiend. Decimal fractions had been employed for the extraction of square roots some 5 centuries before his time, but nobody used decimal numbers in daily life. Stevin declared that using decimals was so important that the universal introduction of decimal weights, measures and coinage was only a matter of time. One of the earliest proposals for a decimal system in which length, area, volume and mass were linked to each other was made by John Wilkins, first Secretary of the Royal Society of London, in his 1668 essay An Essay Towards a Real Character and a Philosophical Language. His proposal used a pendulum that had a beat of 1 second as the basis of the unit of length. 2 years later, in 1670, Gabriel Mouton, a French abbot and scientist, proposed a decimal system of length based on the circumference of the Earth. His suggestion was that a unit, the milliar, be defined as a minute of arc along a meridian. He then suggested a system of sub-units, dividing successively by factors of 10 into the centuria, decuria, virga, virgula, decima, centesima, and millisima. His ideas attracted interest at the time, and were supported by both Jean Piccard and Christian Huygens in 1673, and also studied at the Royal Society in London. In the same year, Gottfried Leibniz independently made proposals similar to those of Mouton. In pre-revolutionary Europe, each state had its own system of units of measure. Some countries, such as Spain and Russia, saw the advantages of harmonizing their units of measure with those of their trading partners. However, vested interests who profited from variations in units of measure opposed this. This was particularly prevalent in France, where the huge inconsistency in the size of units of measure was one of the causes that, in 1789, led to the outbreak of the French Revolution. During the early years of the Revolution, savants including the Marquis de Condorcet, Pierre-Simon Laplace, Adrien-Marie Legendre, Antoine Lavoisier and Jean-Charles de Borda set up a commission of weights and measures. The commission was of the opinion that the country should adopt a completely new system of measure based on the principles of logic and natural phenomena. Logic dictated that such a system should be based on the radix used for counting. Their report of March 1791 to the Assemblée Copyright Nationale Constituante considered but rejected the view of Laplace that a duodecimal system of counting should replace the existing decimal system. The view such a system was bound to fail prevailed. The Commission's final recommendation was that the Assembly should promote a decimal-based system of measurement. The leaders of the Assembly accepted the views of the Commission. Initially, France attempted to work with other countries towards the adoption of a common set of units of measure. Among the supporters of such an international system of units was Thomas Jefferson, who, in 1790, presented a document plan for establishing uniformity in the coinage, weights, and measures of the United States to Congress, in which he advocated a decimal system that used traditional names for units. The report was considered but not adopted by Congress. Original metric system, the French law of 18 Germinal, Year 3 defined 5 units of measure, the Marta for length, the area, 100 am2, for area, of land, the Starry, 1 am3, for volume of stacked firewood, the Litria, 1 dm3, for volumes of liquid, the gram for mass. This system continued the tradition of having separate base units for geometrically related dimensions, for example, Marta for lengths, R for areas, Starry for dry capacities, and liter for liquid capacities. The hectare, equal to 100 ares, the area of a square 100 meters on a side, is still in use. The early metric system included only a few prefixes from milli to myria. Originally the kilogram, defined as being 1 pint of water at the melting point of ice, was called the grave. The gram being an alternative name for 1/1000th of a grave. However, the word grave, being a synonym for the title count, had aristocratic connotations and was renamed the kilogram. The name Marta was suggested by Auguste Savinien Leblanc in May 1790. France officially adopted the metric system on December 10, 1799. Although it was decreed that its use was to be mandatory in Paris that year and across the provinces the following year, the decree was not universally observed across France. International adoption, areas annexed by France during the Napoleonic era were the first to inherit the metric system. In 1812 Napoleon introduced a system known as mesures usuels which used the names of pre-metric units of measure, but defined them in terms of metric units. A euro for example, the livre métrique was 500 ag and the thys métrique was 2 meters. After the Congress of Vienna in 1815, France lost the territories that she had annexed. Some, such as the Papal States, reverted to their pre-revolutionary units of measure. Others such as Baden adopted a modified version of the mesures usuels, but France kept her system of measurement intact. In 1817 the Netherlands reintroduced the metric system, but used pre-revolutionary nomes. A euro for example 1 centimeter became the duim, the ons became 100 ag and so on. Certain German states adopted similar systems and in 1852 the German Zollverein adopted the Zollpfund of 500 ag for intrastate commerce. In 1872 the newly formed German Empire adopted the metric system as its official system of weights and measures, and the newly formed Kingdom of Italy likewise, following the lead given by Piedmont, adopted the metric system in 1861. The Exposition Universelle devoted a stand to the metric system, and by 1875 2/3 of the European population and close on half the world's population had adopted the metric system. By 1872 the only principal European countries not to have adopted the metric system were Russia and the United Kingdom. By 1920 countries comprising 22% of the world's population, mainly English-speaking, used the imperial system. 25% used mainly the metric system and the remaining 53% used neither. In 1927 several million people in the United States sent over 100,000 petitions backed by the Metric Association and the General Federation of Women's Clubs urging Congress to adopt the metric system. The petition was opposed by the manufacturing industry, citing the cost of the conversion. International standards. In 1861 a committee of the British Association for Advancement of Science including William Thomson, James Clerk Maxwell and James Prescott Joule introduced the concept of a coherent system of units based on the meter, gram and second which, in 1873, was extended to include electrical units. On May 20, 1875 an international treaty known as the Convention du Marche was signed by 17 states. This treaty established the following organizations to conduct international activities relating to a uniform system for measurements: General Conference on Weights and Measures, an intergovernmental conference of official delegates of member nations and a supreme authority for all actions. International Committee for Weights and Measures, consisting of selected scientists and metrologists, which prepares and executes the decisions of the CGPM and is responsible for the supervision of the International Bureau of Weights and Measures. International Bureau of Weights and Measures, a permanent laboratory and world center of scientific metrology, the activities of which include the establishment of the basic standards and scales of the principal physical quantities and maintenance of the international prototype standards. In 1881, First International Electrical Congress adopted the BAAS recommendations on electrical units, followed by a series of congresses in which further units of measure were defined, and the International Electrotechnical Commission was set up with the specific task of overseeing electrical units of measure. This was followed by the International Congress of Radiology who, at their inaugural meeting in 1926, initiated the definition of radiological-related units of measure. In 1921 the Meter Convention was extended to cover all units of measure, not just length and mass, and in 1933 the 8th CGPM resolved to work with other international bodies to agree standards for electrical units that could be related back to the international prototypes. Since 1954 the CIPM committee that oversees the definition of units of measurement, the Consultative Committee for Units, has representatives from many international organizations including the ISR, IEC and ISO under the chairmanship of the CIPM. Variants: a number of variants of the metric system evolved, all using the Marcha des archives and kilogram des archives as their base units, but differing in the definitions of the various derived units. Centimeter-gram-second systems: the centimeter-gram-second system of units was the first coherent metric system, having been developed in the 1860s and promoted by Maxwell and Thomson. In 1874, this system was formally promoted by the British Association for the Advancement of Science. The system's characteristics are that density is expressed in gram per centimeter 3, force expressed in dynes, and mechanical energy in ergs. Thermal energy was defined in calories, 1 calorie being the energy required to raise the temperature of 1 gram of water from 15.5 AA degrees Celsius to 16.5 AA degrees Celsius. The meeting also proposed two sets of units for electrical and magnetic properties: the electrostatic set of units and the electromagnetic set of units. Meter-kilogram-second systems: the CGS units of electricity were cumbersome to work with. This was remedied at the 1893 International Electrical Congress held in Chicago by defining the international ampere and ohm using definitions based on the meter, kilogram and second. In 1901, Giovanni Giorgi showed that by adding an electrical unit as a fourth base unit, the various anomalies in electromagnetic systems could be resolved. The meter-kilogram-second Coulomb and meter-kilogram-second ampere systems are examples of such systems. The International System of Units is the current international standard metric system and is also the system most widely used around the world. It is an extension of Giorgi's MKSA Systema. Its base units are the meter, kilogram, second, ampere, Kelvin, candela and mole. Meter-ton-second systems: the meter-ton-second system of units was based on the meter, ton and second. The unit of force was the stheni and the unit of pressure was the psa. It was invented in France for industrial use and from 1933 to 1955 was used both in France and in the Soviet Union. Gravitational systems: gravitational metric systems use the kilogram force as a base unit of force, with mass measured in a unit known as the Hill, Technische Masseinheit, mug or metric slug. Although the CGPM passed a resolution in 1901 defining the standard value of acceleration due to gravity to be 980.665 a centimeter per second, gravitational units are not part of the International System of Units. International System of Units. The 9th CGPM met in 1948, 3 years after the end of the Second World War and 15 years after the 8th CGPM. In response to formal requests made by the International Union of Pure and Applied Physics and by the French government to establish a practical system of units of measure, the CGPM requested the CIPM to prepare recommendations for such a system, suitable for adoption by all countries adhering to the Meter Convention. The recommendation also catalogued symbols for the most important MKS and CGS units of measure, and for the first time the CGPM made recommendations concerning derived units. At the same time the CGPM formally adopted a recommendation for the writing and printing of unit symbols and of numbers. The CIPM's draft proposal, which was an extensive revision and simplification of the metric unit definitions, symbols and terminology based on the MKS system of units, was put to the 10th CGPM in 1954. In accordance with Georgy's proposals of 1901, the CIPM also recommended that the ampere be the base unit from which electromechanical units would be derived. The definitions for the ohm and volt that had previously been in use were discarded and these units became derived units based on the meter, ampere, second and kilogram. After negotiations with the International Commission on Illumination and IUPAP, two further base units, the degree Kelvin and the candela, were also proposed as base units. The full system and name System E International Uniter Copyright S were adopted at the 11th CGPM in October 1960. During the years that followed, the definitions of the base units and particularly the methods of applying these definitions have been refined. The formal definition of International System of Units along with the associated resolutions passed by the CGPM and the CIPM are published by the BIPM in brochure form at regular intervals. The 8th edition of the brochure Le Système International d'Unité Copyright ZAR The International System of Units was published in 2006 and is available on the Internet. In October 2011, at the 24th CGPM, proposals were made to change the definitions of 4 of the base units. These changes should not affect the average person. Relating SI to the real world. Although SI, as published by the CGPM, should, in theory, meet all the requirements of commerce, science and technology, certain units of measure have acquired such a position within the world community that it is likely they will be used for many years to come. In order that such units are used consistently around the world, the CGPM catalogued such units in tables 6 to 9 of the SI brochure. These categories are, non-SI units accepted for use with the International System of Units. This list includes the hour and minute, the angular measures and the historic, non-coherent metric units, the liter, ton and hectare, non-SI units whose values in SI units must be obtained experimentally. This list includes various units of measure used in atomic and nuclear physics and in astronomy such as the Dalton, the electron mass, the electron volt, the astronomical unit and a number of other units of measure that are well established, but dependent on experimentally determined physical quantities. Other non-SI units. This list catalogues a number of units of measure that have been used internationally in certain well-defined spheres including the bar for pressure, the AENNGSTRA paragraph M for atomic physics, the nautical mile and the knot in navigation. Non-SI units associated with the CGS and the CGS Gaussian system of units. This table catalogues a number of units of measure based on the CGS system and dating from the 19th century. They appear frequently in the literature, but their continued use is discouraged by the CGPM. Usage around the world. The usage of the metric system varies around the world. According to the U.S. Central Intelligence Agency's Factbook, the International System of Units has been adopted as the official system of weights and measures by all nations in the world except for Burma, Liberia and the United States, while the NIST has identified the United States as the only industrialized country where the metric system is not the predominant system of units. However, reports published since 2007 hold this is no longer true of Liberia or Burma. An Agence France Presse report from 2010 stated that Sierra Leone had passed a law to replace the imperial system with the metric system, thereby aligning its system of measurement with that used by its Mano River Union neighbors Guinea and Liberia. Reports from Burma suggest that that country is also planning to adopt the metric system. In the United States, metric units, authorized by Congress in 1866, are widely used in science, military, and partially in industry, but customary units predominate in household use. At retail stores, the liter is a commonly used unit for volume, especially on bottles of beverages, and milligrams are used to denominate the amounts of medications, rather than grains. On the other hand, non-metric units are used in certain regulated environments such as nautical miles and knots in international aviation. In the countries of the Commonwealth of Nations, the metric system has replaced the imperial system by varying degrees. Australia, New Zealand and Commonwealth countries in Africa are almost totally metric, India is mostly metric, Canada is partly metric, while in the United Kingdom the metric system, the use of which was first permitted for trade in 1864, is used in much government business, in most industries including building, health and engineering, and for pricing by measure or weight in most trading situations, both wholesale and retail. However, the imperial system is widely used by the British public and is legally mandated in various cases, such as road sign distances must be in yards and miles. Some other jurisdictions, such as Hong Kong, have laws mandating or permitting other systems of measurement in parallel with the metric system in some or all contexts. Variations in spelling. The SI symbols for the metric units are intended to be identical, regardless of the language used, but unit names are ordinary nouns and use the character set and follow the grammatical rules of the language concerned. For example, the SI unit symbol for kilometer is km everywhere in the world, even though the local language word for the unit name may vary. Language variants for the kilometer unit name include kilometro, kilometer, 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 II to the first II to the first IOI 1/4 I micron III, kilocubed metro kilometro, kilocubed metro, and th 3/4 th 1/4 th micron n on euro. Variations are also found with the spelling of unit names in countries using the same language, including differences in American English and British spelling. For example, meter and liter are used in the United States, whereas meter and liter are used in other English-speaking countries. In addition, the official U.S. spelling for the rarely used SI prefix for 10 is dcar. In American English the term metric ton is the normal usage, whereas in other varieties of English ton is common. Gram is also sometimes spelled gram in English-speaking countries other than the United States, though this older usage is declining. Conversion and calculation incidents. The dual usage of or confusion between metric and non-metric units has resulted in a number of serious incidents. These include, flying an overloaded American International Airways aircraft from Miami, Florida to Marquesas, Venezuela on May 26, 1994. The degree of overloading was consistent with ground crew assuming that kilogram weight markings on cargo were pounds. In 1999, the Institute for Safe Medication Practices reported that confusion between grains and grams led to a patient receiving phenobarbital 0.5 grams instead of 0.5 grains after the practitioner misread the prescription. The Canadian Gimli glider accident in 1983, when a Boeing 767 jet ran out of fuel in mid-flight because of two mistakes made when calculating the fuel supply of Air Canada's first aircraft to use metric measurements. Mechanics miscalculated the amount of fuel required by the aircraft as a result of their unfamiliarity with metric units. The root cause of the loss in 1999 of NASA's $125 million Mars Climate Orbiter, which crashed into Mars, was a mismatch of units. The spacecraft engineers calculated the thrust forces required for velocity changes using U.S. customary units, whereas the team who built the thrusters were expecting a value in metric units as per the agreed specification. Conversion between SI and legacy units. During its evolution, the metric system has adopted many units of measure. The introduction of SI rationalized both the way in which units of measure were defined and also the list of units in use. These are now catalogued in the official SI brochure. The table below lists the units of measure in this catalogue and shows the conversion factors connecting them with the equivalent units that were in use on the eve of the adoption of SI. The SI brochure also catalogues certain non-SI units that are widely used with the SI in matters of everyday life, or units that are exactly defined values in terms of SI units and are used in particular circumstances to satisfy the needs of commercial, legal, or specialized scientific interests. These units include future developments. After the meter was redefined in 1960, the kilogram was the only SI base unit that relied on a specific artifact. After the 1996–1998 recalibrations, a clear divergence between the international and various national prototype kilograms was observed. At the 23rd CGPM, the CIPM was mandated to investigate the use of natural constants as the basis for all units of measure rather than the artifacts that were then in use. At a meeting of the CCU held in Reading, United Kingdom in September 2010, a resolution and draft changes to the SI brochure that were to be presented to the next meeting of the CIPM in October 2010 were agreed to in principle. The CCE proposed to, in addition to the speed of light, define four constants of Natura Planck's constant, an elementary charge, Boltzmann constant and Avogadro constant to have exact values, retire the international prototype kilogram, revise the current definitions of the kilogram, ampere, Kelvin and mole to make use of the above four constants of nature, tighten the wording of the definitions of all the base units. The CIPM meeting of October 2010 found that the conditions set by the General Conference at its 23rd meeting have not yet been fully met. For this reason the CIPM does not propose a revision of the SI at the present time. The CIPM did however sponsor a resolution at the 24th CGPM in which the changes were agreed in principle and which were expected to be finalized at the 25th CGPM in 2014. See also, binary prefix, used in computer science, conversion of units, history of measurement, ISO IEC 80000, style manual for measurements metric and non-metric, superseding ISO 31, metrication, the process of introducing the SI metric system as the worldwide standard for physical measurements, metrology, units of measurement, notes. References. External links, CBC Radio Archives for Good Measure, Canada converts to metric.